Hey everybody, sorry I couldn't be here, but just know that you're in really good hands with my substitute, Mike Merritt of the Utah Community Forest Council. Now, as you may know, the popularity of automation is really on the rise. So actually, because I was not able to be here, I've decided to let my virtual arborist self teach Chapter 9 this year. Go ahead and say hi, virtual arborist Daniel.
Hi, virtual arborist Daniel.
I don't know if that's going to work so well. Maybe I'll just draw it. But just keep in mind, if you have any questions as we go through this presentation, be sure to write them down, and then you can either email them to me afterwards or ask Mike. Between the two of us, we should be able to get you squared away. The title of this chapter is Tree Support and Lightning Protection, so we'll break it down into these two concepts. First off, tree support. Basically what you need to know is that tree support is the installation of hardware in a tree. This is done in order to provide supplemental support by limiting movement when the strength of an entire tree or tree part is in question. Tree support is generally employed when a tree has a weakness that may create a higher risk of failure. This includes codominant stems, multi-stem trees, weak-wooded trees, or excessively heavy limbs. Tree support can take the form of cabling, bracing, guying, or propping, and we'll discuss each of these in turn. When properly installed, tree support can increase the lifespan and decrease the risk of failure for a compromised tree, which are both good things. However, it must be kept in mind that support does not eliminate hazards altogether. It just reduces risk to a tolerable level. The next thing to remember is that a tree needs a thorough assessment beforehand in order to determine its suitability for tree support. We need to be able to answer questions such as, what is the risk? Can support actually mitigate the hazard? If the tree contains seriously defective limbs, an excessive amount of decay, or the root system is not structurally sound, the answer is most likely no. Are there other strategies for addressing the hazard, like pruning or removal? Remember, anytime we install hardware into a tree, we are changing its response to loading and potentially opening it up to decay. So we need to feel confident that the tree will respond well to support. The actual installation of tree support systems must follow ANSI standards found in the ISA's Best Management Practices for Tree Support, which covers all of the specific size, weight, and strength factors involved in tree support applications. At this time, however, we will only be covering the general features of tree support to impart the basic understanding you'll need for the exam. We'll begin with cabling, or static cabling. In this technique, cables are installed between two or more limbs in a tree to limit movement of limbs with weak branch connections or to support heavy limbs. When cabling, support can be maximized by installing the cable directly across the union being supported, in line with the hardware and at least 2/3 up. Again, we'll want to place our cable approximately 2/3 the distance from the weak attachment to the end of the limbs to be cabled. The branches must be large and solid enough to provide adequate support, but far enough from the crotch to utilize leverage as an advantage. We'll want our cable to run directly across the union, which is perpendicular to its horizontal front to back axis. Our cable attachments must also run in line with the cable, which means they are generally attached at an angle through the limb as opposed to straight through the limb. Once installed, the cable should be just taut, not too slack and not too tight. Too loose and the cable will not be effective. Too tight and the hardware may pull out. A come-along or mechanical advantage is useful for achieving proper tension by bringing the limbs slightly closer together for installing the cable and then being released. Cables are most commonly installed in a simple or direct arrangement. This means one cable between two limbs. At times, however, if more than two stems need cabling, a tree will require more than one cable. Extra stability can be added to the system by cabling branches together in triangular combinations. If more crown movement is desired, a box or rotary system can be installed. A hub and spoke system can connect multiple leaders while allowing for some independent movement, although it is the most complex configuration to install. When more than one cable is being installed on the same limb, space the hardware no closer than the distance of the diameter of the limb and never in vertical alignment with other hardware. Now that we understand the overall technique, we need to review some basic hardware and tools used for static cabling. It may be helpful to break this down into anchor hardware, cable types, cable terminations, and cabling tools. After this, we'll wrap this section up by discussing a newer alternative to cabling with metal cables. Anchor hardware is used to connect the tree limb to the cable, and it requires drilling a hole into or through the limb. Machine-threaded anchors, such as eye bolts or threaded rods with Allen eye nut, pass through the limb and are generally preferred over lag-threaded anchors, which merely screw into the wood. Machine-threaded anchors require a drilled hole which is 1/16 to 1/8 of an inch larger than the threads. Also, heavy-duty or heat-treated bolts and washers are strongly recommended in conjunction with these anchors. Finally, anchor hardware must never be installed closer than 1 branch diameter or 12 inches apart, whichever is a smaller distance, and, if at all possible, they must not be in vertical alignment either. Never install more than 1 cable on each anchor. Lag-threaded anchors, such as a lag eye or lag hook, have larger threads which actually screw into a pre-drilled hole that is 1/16 to 1/8 of an inch smaller than the threads. This type of anchor hardware is limited in application to smaller limbs up to 10 inches and cannot be used in the presence of decay, or in weak or decay-prone wood. Regardless of type, anchors should be installed in a direct line with the cable to maximize strength. This means the installation angle will rarely be perpendicular to the limb. When it comes to cable types, there are really only 3 types of metal cables suitable for tree support, all of which come in a variety of sizes. The first is 7-strand common grade cable. This cable is relatively flexible and easy to work with, and inexpensive. Extra high strength, or EHS cable, is the second type of cable that is commonly used in tree support. As the name implies, it is much stronger than common grade cable, but it is also much less flexible and requires special hardware for attaching it to an anchor. P.S. Both of these first 2 types of cable are composed of 7 strands. Aircraft cable is the third type of cable, but it is used almost exclusively in Australia and the United Kingdom. It's composed of 7 strands with 19 smaller strands inside. It has the benefits of being strong and flexible, with the drawback of having limited attachment options. Cable termination is another way to describe how a cable attaches to the anchor hardware, and each of these cable types employs a different method of attachment. Anytime a cable is attached to anchoring hardware, a heavy-duty thimble needs to be incorporated into the termination. The purpose of the thimble is to create an eye which protects the cable from abrasion and increases the bend radius of the cable, which makes the attachment stronger. 7-strand common grade cable can be attached to the hardware using an eye splice. This is achieved by wrapping the cable around the thimble, then separating the cable strands beyond the thimble and individually wrapping them back around the cable above the thimble. Extra high strength cable uses one of 2 terminations. The first is called a dead end grip and is a manufactured spiral wrap required because EHS is too stiff for splicing. Dead end grips do need thimbles and are not recommended for situations where the tree will be subject to dynamic loads caused by twisting and swaying in gusty winds. If using this termination, it is important to take into account the wind conditions and potential for swaying. The second, less common type of manufactured termination for EHS cable is a cable stop, which is a metal knob affixed to the cable after it runs through the drilled hole in a limb. Thus, cable stops preclude the need for anchor hardware. For aircraft cable, terminations are made using metal swages, which are crimped to the cable to make an eye, after being wrapped around a thimble, of course. Next in our discussion are some common tools for cabling of trees. As already mentioned, a come-along or mechanical advantage is very useful for creating the proper tension by bringing limbs to be cabled closer together. A cable grip helps the arborist handle the cable and pull it into place for attachment. A cable aid is a useful little tool which can open thimbles, tighten lags, and help wrap dead-end grips onto the cable. To install hardware into the tree, holes must be drilled. Since cords can be an issue, gasoline-powered drills are generally preferred, but cordless drills can, in some cases, have enough torque to drill through the limb. Regardless of drill type, a ship auger bit should be used in tree support applications. Just make sure it's sharp. Other tools which are useful in cabling operations are hacksaws, hammers, chisels, mallets, slings, and cable cutters. The climber must be able to carry all tools safely in a bag, bucket, or belt to prevent them from accidentally being dropped. Now that we've gone over all the techniques of static cabling, it might be a good time to mention the fourth cabling option, dynamic cable systems. These synthetic cables have been recently developed as an alternative to more rigid metal cables and require much less in the way of hardware and tools to install because they simply wrap around limbs. Dynamic cables allow for more tree movement, which in turn allows the tree to develop reaction wood, becoming stronger in time. Potential drawbacks to dynamic cables are UV light degradation of the polypropylene over time, the need for a lateral branch to rest on, and the potential to constrict limbs. Care must be taken when installing dynamic systems to prevent girdling the limb at the point of attachment. Bracing is the next topic in our tree support discussion. It is the use of steel rods in limbs, leaders, or trunks to provide support for a union. Bracing is used to reinforce weak crotches or to strengthen decayed areas. In most cases, bracing is used in combination with cabling, not as a substitute. There are two types of rod that can be used for bracing applications: lag-threaded rods and machine-threaded rods. As you may have guessed, lag-threaded rods can be screwed directly into a tree without the use of bolts or washers and require a hole that is 1/16 to 1/8 of an inch smaller than the threads. Though this is a simpler process, lag-threaded rods should be kept to smaller stems, 10 inches or less. Machine-threaded rods are the proper choice for large trees, weak-wooded trees, or decayed wood. These rods require a hole that is 1/16 to 1/8 of an inch larger than the threads and also require heavy-duty or heat-treated washers and nuts to secure them to the tree. To create the hole, use a drill bit that is long enough to penetrate all the way through the sections being braced. Never attempt to drill from opposite ends and hope to have the holes align, as this is practically impossible. In many cases, it may be necessary to install more than one bracing rod. If more than one bracing rod is to be installed, stagger them longitudinally if possible. Also, as with anchoring hardware, space rods at a distance greater than the diameter of the wood being braced, or 12 inches, whichever is less. Once the hole is drilled, a mallet or small sledgehammer may be required to drive the machine-threaded rod through the tree. With the rod in place, you are now ready to attach the washers and nuts. Seat the washers directly against the bark. However, if the bark is thick, use a chisel or Forstner bit to countersink the washer against the wood, but not into the cambium. Cut off any excess rod beyond the nuts and peen the end of the rod to prevent the nuts from backing off. Please note that these last few steps of seating the washers, trimming the rod, and peening the ends also applies to the installation of anchor hardware. Guying is the installation of cable between a tree and an external anchor to provide supplemental support and reduce tree movement. This technique is appropriate for trees that have serious root defects but cannot be removed due to their cultural importance. Guying is also useful to keep trees upright when there is concern that a tree may fall in the direction of a target. It is important to remember that guying tends to be permanent because the tree will likely come to depend on this mechanical support. Guy wires can be attached to trees using the same methods for installing cables, but must be attached above the midpoint of the tree. Also, the arborist must be certain that whatever is being used as an anchor has more than enough strength to support the tree, even in wet or windy conditions. A ground anchor must be no closer than 2/3 the distance between the ground and the lowest attachment in the tree. When using a tree as the anchor, attach the guy on the lower half of the anchor tree and on the upper half of the supported tree, preferably 2/3 of the way up. A significant consideration in the installation of guys is public safety. Tree-to-tree guys should be installed high enough to reduce the risk of any hazards, including pedestrian or vehicular traffic. Tree-to-ground guys should be clearly marked and protected from inadvertent contact. Propping is the installation of rigid structures between the ground and a branch or trunk to provide support. Typically, props are used under branches that are nearly horizontal or downward growing. There is not much information about the use or design of props in arboriculture, and there are many designs. Some key factors in prop design are that it will not restrict future growth of the limb, that it has sufficient strength to fully support the load, and that there is some type of provision for keeping the branch from falling off the prop. We have now come to the second half of our chapter, lightning protection. Lucky for you, there's not as much material to cover here. Before we begin, let's look at how lightning affects trees in the first place. When an unprotected tree is struck, lightning may travel down the stem for a distance and then jump out to a more conductive tree, structure, person, or animal. This phenomenon is called side flash, and it can be very destructive. That said, lightning usually exits a tree through the roots, where it dissipates into the soil. When the charge is dissipated, it creates a great difference in the electrical potential at the soil surface. This is known as step voltage. If a person is standing in the area, step voltage can send a lethal current of electricity through their body. Most of the time, lightning does not kill a tree, and in some cases, there are no visible injuries. However, lightning often causes internal injuries to the tree, which may increase tree stress and reduce water conducting capacity. This in turn will generally make the tree more susceptible to pest attacks, decay, and drought stress. Trees affected by lightning should be closely monitored to look out for potential problems and hazards, but extensive arboricultural treatments should be delayed for a year or more. Trees that are a good candidate for lightning protection include trees of historic interest or high economic value, tall trees close to houses or buildings, or large trees where people often congregate. Keep in mind that lightning is more likely to strike the tallest tree in a group. A lightning protection system is simply a copper conductor that extends from the top of the tree down the trunk and out into the soil where it is grounded. These systems consist of three components: an air terminal, conductors, and a ground terminal. Though the detailed ANSI standards for installation of lightning protection systems can be found in the ISA's Best Management Practices booklet, we'll review the basic process. An air terminal needs to be placed as high on the tree as possible. The main conductor is a copper cable attached to the tree at 3 to 6 foot intervals running down a major limb and the trunk. The conductor path should follow the natural shape of the tree, avoiding sharp bends, kinks, and crotches. If a tree is larger than 35 feet in crown radius, secondary conductors, which tie into the main conductor, are recommended. The main conductor travels down the trunk and to the ground, where it is then buried in an 8-inch deep trench, running out from the trunk approximately 10 feet. At this point, the main conductor is connected to a ground terminal, which consists of a rod or plate fixed into the ground. Ground terminals must not be installed within 2 feet of a building's foundation or any other underground installation, such as utilities. Even though lightning protection systems are very effective in preventing tree damage, these systems are not intended to directly protect people from lightning strikes, side flash, and step voltage. Protected trees cannot be considered safe havens from lightning strikes during storms. All right, so there's one very important point that needs to be made in closing. The installation of tree support systems or lightning protection systems represents an ongoing responsibility to the arborist. Basically, any time that these are installed, we need to explain to the clients that a periodic inspection needs to be done. If any faults or changes have happened when we inspect these, then we need to go back and repair and revamp our system, okay? And last thing, if it's found that any major changes need to be made or additional cables need to be installed, generally it's preferable to leave the old systems in place until the new systems have been installed. And even then, generally we leave the old systems in place. But actually that's about it for our presentation today. Thank you for watching, and hope to see you in the trees.